So I guess that Tuesday's exam was so exhausting that the majority of the class couldn't face coming to class today. I think this is the lowest turnout I have seen by a long way. Maybe we should have an extra credit as part of the... I'm very tempted to be quite honest. Okay, so first of all, an announcement. So I forget now, maybe a week ago, just over a week ago, I asked for you, some of you to sign up to participate in this MyShake project that we have, and some of you did, so thank you to those of you who did. Chinkai released the app to those of you who signed up on Monday, but only some of you downloaded the app. So I guess the first thing is to appeal to those of you who signed up and are in the room to put the app on your phone so we can see how it performs. And then the second thing is if you do have an Android phone and you didn't sign up, then please do consider signing up. All you have to do is download this app onto your phone. It is not going to impact what you do on your phone in any way. It's a very low-power app. It just runs in the background on your phone, and so it has no impact. I mean, we were very careful, of course, to engineer it that way. It has no impact on what you're doing on your phone. So please, what was the email? Chinkai, let me write it down. Okay. So if you would like to sign up, please do send an email to... No, sure. Thank you. MyShake 2014@gmail. So yeah, so please do consider signing up, participate in it. It's the beginning of something big, so please do consider participating. So was there a question? Yeah. Sorry, say again? Absolutely. Yeah, no, in fact, that's absolutely fine. That's a really good point. We should do that. So friends and family are welcome. Okay, so please do. I can't believe we didn't think of that. All right, that is a fabulous idea. You get extra credit for sure. Please, yeah, if you have friends or family and you would like to encourage them to participate, you can obviously tell them about the project. Ask them to send an email to myshake2014@gmail.com, and Chinkai will add them to the authorized users, send them a link so they can download the app. Chinkai is also here, so if any of you are having problems either downloading the app or if you have questions about it, he'd be happy to answer them and help you install it on the phone. I think if you have other problems, just send an email to that address, right? Yeah. So if any other problems, just send an email to that address. Yeah. So the question was, are we going to try and do it for an iPhone? In the long term, absolutely. In the short term, not at all. So we can only handle one operating system to start with. So that's why there are reasons we chose Android. So the goal would be to have this on any kind of mobile device in the future, but this is obviously a research project, so we just want to get working on one platform first. And I'm an iPhone user, so I hate to admit this, but Android is bigger than iOS. Okay. A couple of other announcements. We have a field trip this weekend. I think Cheng sent out an email following the midterm on Tuesday. It's the same drill as last time. There are 10 slots to sign up for the field trip. If you haven't signed up, the vast majority of you have. If you haven't signed up, please do sign up for a time slot. You just have to go on one, obviously. There are time slots on Friday, Saturday, Sunday, and Monday. There is a slight difference with this field trip in that we will not be meeting on campus. Okay? So we will be meeting at the intersection of Spruce and Glen. Okay? So this is, you go to the class website and you click on the field trips link on the left-hand side. You'll see field trip 1, field trip 2. This is what you see when you click on field trip 2. So Spruce and Glen is right here. So this is campus. This is the north gate of campus where everybody met for the first field trip. And it's about a sort of 10, 15-minute walk to get to this point, which is where the field trip will start. So if you signed up for the 9 o'clock field trip, then we will meet at Spruce and Glen at 9:20. The point is, if you signed up for the 9 till 11 time slot, that's the time period you need. If you leave campus at 9, you'll be at Spruce and Glen by 9:20. We'll be done by about quarter to 11, so you can be back on campus at 11 o'clock. Okay? That's how it works. So yeah, you should go on to BSpace, the section tab of BSpace, and sign up for a slot. So yeah, questions? Yeah, so we will end back where we started. We'll be doing a kind of loop up here, and we will end back here. And as I say, we should be done at about quarter to 11, so the idea is you can be back on campus. You'll be away from campus for about 2 hours in the future slot. Yeah. So you sign up for 9 o'clock, that means you need to be at Spruce and Glen at 9:20. You sign up for an 11 o'clock trip, then it's 11:20. Okay, any other questions? Okay, wow, that's easy. All right. Okay, so we are in the final third of the class. Hallelujah. So the final third of the class is really shifting the focus a little bit again onto practical ways that we can start to mitigate the effects of earthquakes. Okay, so that's what this final third of the class is. The first third was kind of historical lessons, scenarios, really motivating what we're doing. The middle third was sort of the science of earthquakes, and then this final third is the applications. How can we reduce the impacts of future earthquakes? And so it obviously ties into the field trip. The field trip is about landslides, the effects of landslides. And the landslides that we'll be looking at are sort of related to earthquakes in a sort of indirect way, and we'll explain that on the field trip. But the point is that on the field trip, you will see how people's houses are slowly falling apart because they are on landslides. And so we will not only see the effects of these landslides on people's homes, but we'll talk about what we can do about it, and what the homeowners can do about it, and the practical realities of dealing with the fact that you own property in a hazardous location that is going to be damaged, and how we're going to handle that. So that's why the field trip is in the final third of the class. The first 3 lectures for this final third are earthquake prediction, earthquake forecasting, and earthquake early warning. So that's today. Remember, Tuesday is actually a holiday, so there'll be no lecture on Tuesday. So then next Thursday and the following Tuesday will be these 3 lectures. And what's important here, and you all know this, that we cannot predict earthquakes. So I want to talk about the earthquake prediction problem, obviously. And then we'll talk about earthquake forecasting, which is something that we can do. And then we'll talk about earthquake early warning, which is also something that we can do. So that's kind of how we're going to move into this final third of the class. Yeah. Sorry, say again? Somebody's already thinking about the final part of the class. Yes, the final exam will be cumulative. Okay, so earthquake prediction, something that we cannot do. I want to take you through a scenario where, well, it's not a scenario, it's something that actually happened when there was an earthquake prediction. And this was by Ivan Browning, and the impact that Ivan Browning had on Missouri. But this is a story that happened, a number of years ago at this point. But this is, and I like it, well, you'll see why I like it in a minute, but I wanted to make the point that this is still an issue. This is an email I received, it's a year ago now. I happened to receive this the day that I was giving this lecture last year, November the 13th, or November 11th, sorry, 2013, right? And this is from a gentleman called Les Brown, who calls him the earthquake alert guy. And he fairly frequently emails me, along with a number of other folks, to predict earthquakes. And so this is the prediction that he sent about a year ago, and he calls it the official prediction for a major earthquake strike in California or the West Coast before December the 29th. A little bit of background before I show you his prediction. There had just been a typhoon that caused significant damage on the other side of the Pacific. Fairly major typhoon, and there was a significant impact of this typhoon, not only immediately, but in the aftermath. A lot of infrastructure was destroyed, and there was issues about getting basic aid, food and water aid to people who had no access to food and water in the days after this particular event. Okay, so back to Les Brown. So the dangers are currently so great from all of the brand new major earthquake energy just generated from the landfall of the super typhoon that it's now necessary to file this official prediction with the California and National Earthquake Prediction Evaluation Councils. It's highly unlikely that the bulk of this huge new earthquake energy will affect us in California or the West Coast. However, the chance does exist just the same. The landfall of the super typhoon in the Philippines heading northwest-northwest had winds speeds reported up to 195 miles per hour. In brief, the landfalls of similar huge windstorms, Yasi, well, I'm not going to read all of these names, Debbie, I can manage that one, all resulted in some of the biggest major earthquakes in all of history. Okay? I'm not going to keep reading this, you can read it in the lecture notes. This particular gentleman believes that earthquakes are caused when typhoons hit landfall. And in the past, as you'll see in a moment, I've received many predictions from him. For example, when hurricanes have hit the Louisiana coast, like Katrina, like Hurricane Katrina, his hypothesis is that you have these big storms that have a lot of energy, they hit a coastline, and that energy is then transferred into the land mass, and it continues along the same path that it was taking when it hit the land, and then you get earthquakes kind of along that line. Okay? Obviously, it's not a great model, but that's his model. And so he claims here that major earthquakes have followed these other typhoons or hurricanes hitting landfall, and so there's a possibility of major earthquakes as a result of this particular one. So this is a prediction, right? He's predicting earthquakes. So what should we do? What should we do with this prediction? What would you do? So the comment here is ignore it. Anybody else? Why would we ignore it? All right, I like that. A lot of correlation, not much causation. I would rephrase it a little bit. He's claiming correlation. He's not, and what the question would be is the causation. I would say there's also a question of whether there's actually correlation. Anybody else? Other thoughts? I mean, let's turn the question around a little bit. There is a California Earthquake Prediction Council, I'm not using the right name, and a National Earthquake Prediction Council. So these are committees of scientists who are technically responsible for issuing earthquake predictions. And more to the point, if they don't issue an earthquake prediction, there's potentially a significant impact. Right? So it's not like you can just ignore it. If there was an earthquake, there would be a problem. So we have to take these kinds of things very seriously. Yeah. Right. So okay. So we could start to think about physical models. We could estimate the energy that's associated with the storm. We could try to estimate how much of that energy might get transferred to the solid Earth surface. That's right. So we could start to ask questions about physical models and whether there's a physical model that can connect one particular process to another process. Right. In this case, hurricanes to earthquakes. That's right. Anything else? Okay. So as I mentioned, this particular gentleman frequently predicts earthquakes, and I did a quick search of my inbox, and it turns out that lots of messages from him that all get automatically filed away by my email. But so he frequently, whenever there's a storm, he predicts there's going to be an earthquake. So to come, you actually hit on all of the important points. So to come to the first question is, well, we should be doing some fact-checking here, right? And so the correlation and causation, the first question is there actually a correlation? So on what dates did hurricanes actually hit coastlines? On what dates did earthquakes occur? And try to understand if there's even a correlation. And I can tell you there is no correlation whatsoever. Okay? So the first thing to do is to start fact-checking, gathering data. Let's have some real data before we start to talk about whether a particular earthquake prediction, or for that matter, whether a particular approach to trying to predict an earthquake might make sense. The second question is there a correlation between these events? Okay, so is there now a correlation between when a hurricane hits the coastline and when there is an earthquake that follows it? How unusual is that? You have to ask the question, how many earthquakes are there generally? Okay, I can give you a guaranteed earthquake prediction. I am confident there's going to be a magnitude 8 next year. Okay, how can I make that statement? Is that a bold statement from a seismologist? I'm hearing some people say yes. I mean it. I'm predicting there's going to be a magnitude 8 next year. Why can I say that? Right, when you look at the earthquake statistics, we talked about this in the context of the Gutenberg-Richter relationship. The average number of magnitude 8s per year is 1. So I guess I could be wrong, but it's very unlikely that I would be wrong. There will be a magnitude 8. So that comes to the question of, well, what do you really mean? You have to say, first of all, you have to say what magnitude, you have to say when, you have to say where, and you have to be able to say, so is this unlikely just based on a random distribution of earthquakes? So we know statistically there's going to be 1 magnitude 8 per year. That means that there's probably about 10 magnitude 7s per year, etc., etc. So you have to ask the prediction that's being made, is it statistically outside of the norm? Okay, so that's kind of coming to this correlation question between these events. And then, of course, the final step is there a causal physical mechanism? I mean, this is what's at the heart of good science. Okay, it's one thing to collect data, it's another thing to identify correlations, but the silver bullet here is actually understanding the physical mechanism. And the reason for that is it's only when we understand the physical mechanism, the physical connection between one process and another process, or one event and another outcome, is if we understand the physical mechanism, then we can start to predict what might happen, right? We need a model, a physical model, to predict what's going to happen. That's what elastic rebound theory is, right? Elastic rebound is a physical model about stresses on the tectonic plates, the build-up of strain, and then how that strain is released. So it's a physical model that fits the data, and then we can use it to start to predict what's going to happen in the future, and that's exactly what we do when we talk about earthquake forecast. Okay, so these are the key elements to sort of understanding this problem and to sort of tackling scientific problems in general. Any questions, comments, before we move on to Ivan Browning? No? All right. Okay, so let me tell you the story of Ivan Browning and his earthquake prediction and the effects of that earthquake prediction. First of all, I'm going to assume you all know where Missouri is. Anybody not know where Missouri is? I'm willing to admit to it. But what? Okay, one person. I'm actually admitting to not knowing where Missouri is. Okay, Missouri, right, is located right on this. This is a seismic hazard map, which I think I've shown you before. Have you seen this map before? No? Okay. All right. So this is the seismic hazard map of the US. It's actually the product of earthquake forecasting, which we're going to talk about in the next lecture. So we'll talk about this in more detail. But the red zones are the places where we expect to have earthquakes. The white zones are the places where we're least likely to have earthquakes. And not surprisingly, the West Coast, the San Andreas fault system, subduction of the Cascadia, beneath Cascadia, are high hazard regions where we expect to have earthquakes. But you can see that there are also bullseyes of high likelihood in some parts of the eastern United States, most notably in what's called the New Madrid seismic zone. Okay? And the reason that the New Madrid seismic zone has this high risk associated with it is that there were three large earthquakes, magnitude 8 plus earthquakes. We estimate they were magnitude 8 or greater earthquakes in this New Madrid seismic zone in 1811 and 1812. Okay? And this caused significant damage. The Mississippi flowed backwards for a short period of time. A lot of destruction throughout the region. We have estimates based on these records of what the shaking intensity looked like. And so this is where the earthquake was located, intensity 10 in here. And then the shaking was felt all the way out to Boston, for example. So the shaking was felt over a very large area. And it's based on these kinds of reports that we're estimating what the magnitude of the earthquake was. Okay, the first seismometer in the Western Hemisphere was installed here at UC Berkeley in 1887. So there are no instrumental records of this particular earthquake. All we have is these written records of the effects of the earthquake. And so people have estimated the magnitude and come up with these kinds of maps. So three big earthquakes in the New Madrid seismic zone. And that's why there's this big bullseye in the hazard map. I can tell you that this bullseye is very controversial within the scientific community. Is this real or is it not? And the reason that it's very controversial comes back to the 3 points on 2 slides ago, that we do not understand the physical mechanism for these earthquakes. We understand why we have earthquakes over here. It's plate tectonics. It's elastic rebound theory. We have a physical model and we understand it. There's no plate tectonics here in the sense that this is in the middle of a plate. So whatever is causing these earthquakes, these vertical motions associated with these earthquakes, are not part of this plate tectonic paradigm, and so we do not understand it very well. And as a result, many seismologists argue that this big bullseye is erroneous and it's not really a fair assessment of the seismic risk in this region. Yeah. Yeah, great question. So on Hawaii, you can see higher risk beneath the main island, lowest risk the most distant island, and that's exactly right. So the earthquakes in Hawaii are being driven by the volcanic processes that we were talking about. The active volcanic processes are on the Big Island, and that's why the hazard is highest on the Big Island, and it's lowest on the most distant island. Exactly right, good observation. Okay, so there is a bullseye. There are reasons that people are concerned about seismic hazard in the New Madrid seismic zone, although it remains a controversial observation. Okay, so to Ivan Browning and what happened. So the first thing was that there was an earthquake with a hint of more to come. And so in September of 1926 and 1990, there was a magnitude 4.6 in southeast Missouri. Okay? 4.6 isn't very big. You wouldn't expect much damage from a magnitude 4.6. Maybe you get a little bit in Missouri just because buildings are not built to the same standards that they're built on the West Coast, where we expect to have earthquakes, but it's obviously pretty minor. So this is a bit of a blip, nothing too unusual. There are a fair number of small magnitude earthquakes in the New Madrid seismic zone, so this is not too far outside of the norm. Okay, so little damage. Certainly nobody was killed by this earthquake, but this kind of woke people up psychologically when they started to think about earthquakes. And then sort of this is where the news media came into play. Somebody kind of noticed that some guy had predicted an even bigger earthquake for December, as in a few months after this relatively small magnitude earthquake. And so there was this vague prediction of an earthquake around December the 3rd. Okay, and people started to pay attention to it. I mean, this is kind of like the earthquake guy emails. You saw how many I got. But they're out there. If there was some reason that people wanted to start being worried about earthquakes, they might point to one of those emails and say, oh my goodness, somebody's predicting an earthquake. And people would take more notice than they would do normally. And so the immediate response here of, well, we should just ignore it. You'd be less likely to ignore it if you just had some kind of earthquake. And so who was it who made this prediction? It was Ivan Browning. And supposedly he had successfully predicted the Loma Prieta earthquake, which of course had occurred the previous year in 1989. He claims that. There's actually no documentation of him predicting the earthquake whatsoever. So who is this? Well, he's a doctor. Apparently that's a big deal. And he's a meteorologist. So obviously has lots of expertise when it comes to the solid earth and earthquake processes. But people, for some reason, well, I know why there's this association. When it comes to the news, and local news, who is it who's talking about earthquakes or any earthquake activity? It's always a meteorologist. I never really understood why this is. I guess of all the people who work at a local news station, it's probably the person that has the most scientific background, although that may well be very limited. It's also the person who's used to looking at maps, maybe. When people talk about earthquakes, of course, they pop them on the map. But this association with meteorology is a little odd. So he argued that earthquakes were triggered by the gravitational attraction of the moon and other planets. So he's putting out a physical model. He's saying that, look, this is how this happens. The reason that this happens is that the gravitational attraction of the moon and the planets, when it aligns, it increases the likelihood of earthquakes. And he's actually talking about alignment of all of the planets. And that happens every 179 years. Okay? So that was the basis for his prediction. And so he was saying that the next peak was on December the 3rd, 1990. The next peak being after the 1811 earthquake, 1811 and 1812 earthquake. If you take 1811 and you add 179, you get 1990. Okay? So that's the basis of his prediction. And so what he actually said, and this is in writing, is 50% chance of a magnitude greater than 6 earthquake within 5 days around December the 3rd. That was his prediction. A lot of people started to pay attention following this September earthquake that a lot of people felt. Okay, ingredient number 3. Unfortunately, this involves a seismologist. Ingredient number 3 was a local seismologist said that there might be something to it. Okay, David Stewart, who's the director for the Center of Earthquake Studies in the region at the University of Missouri, I forget now exactly where that is, it still exists. He urged the public to keep an open mind and that perhaps the earthquake prediction was worth looking at. I don't think any seismologist would make a statement like that today. The National Earthquake Prediction Council, maybe this was a forerunner to it, but they formed a committee to take a look at the evidence and actually to come out with a conclusion based on the evidence.